Aim. This experiment is to study the effect of force of different magnitude on bending stress in beam. Theory. When an external load or the structural load applied in the beam is large enough to displace the beam from its present place, then that deflection from its recent axis is called bending of beam. Bending stresses. Applied force when produced bending in beam also produces stresses in beam. These are called bending stresses. Bending stresses are produced in a beam when an external force is applied on the beam and produce deflection in the beam. Bending stresses may mainly depend on the shape of the beam, length of the beam, and magnitude of force applied on the beam. In order to calculate the bending stresses in the beam, following formula can be used: E is equal to sigma by epsilon, where E is equal to Young's modulus, m is equal to bending moment, I is equal to second moment of inertia, sigma is equal to bending stress, epsilon is equal to bending strain, and y is equal to distance from the neutral axis. Calculation. According the equation shown above, for calculation bending stresses and strain, there are certain quantities like area of cross section of beam sections and second moment of inertia of beam needed to be known. Formula: y bar is equal to a1 y1 plus a2 y2 over a1 plus a2. Ixx is equal to bdq by 12 into a into y bar minus y का whole square. B is equal to breadth, D is equal to depth, y bar is equal to distance of center of gravity of a hole from origin. Sigma is equal to my over I theoretical. Sigma is equal to epsilon E experimental. Experiment 2. To verify Euler's buckling equation for struts of some material and length to different end conditions. Theory. Buckling is of concern wherever a slender material is under compression. There are usually two primary concerns when analyzing and designing structures. One, the ability of the structure to support a specified load without expressing excessive stress, and two, the ability of the structure to support a given load without undergoing undesired deformation. A column will buckle when it is subjected to a load greater than the critical load. Therefore, instead of remaining straight, it will suddenly buckle. A Swiss mathematician, Leon had Euler, created a formula that predicts the maximum critical axial buckling load of a strut. The Euler's relation gives the crippling loads for columns and struts for various end conditions. PE is equal to pi square EI over LE square, where PE is equal to crippling load or buckling load Newton. E is equal to Young's modulus of elasticity, which is in gigapascal. I is equal to second moment of inertia, which is millimeter raised to 4, and LE is equal to effective length meter. Factors affecting buckling of a strut: the second moment of area I is measured of both the cross-sectional area and shape. It affects the stiffness of the strut. Elastic bending of a strut depends on the Young's modulus E of the material it is made from, so E value affects the buckling load. Procedure: measure the thickness, width and length of the strut, connect and switch on the load display and place the strut in the desired end conditions. Tap the load moving and to remove any effects of friction. Then the display by pressing F1 button provided on panel. Loosen the 4 screens securing the loading and slide it along the base until you fits 4 end conditions you need. Retighten the 4 screws. Connect data transfer cable with the computer and panel provided. Run the simulation software and the software will create your results table for you automatically. Use the large hand wheel loading, which is 7th point. Screw 7th point is use the large hand wheel loading screw to apply a small force to the strut. Check that the strut bends. 8th is carefully add a small load to the strut. This helps to check the end fittings are holding the strut surely, especially if you are testing with the find and conditions. As you turn the hand wheel, watch the loadings, reading and deflection of the strut. When you see the load does not increase but the struts is start deflecting, the strut has buckled. The load Newton starts increasing to a certain value, after which it continuously decreases, provided that the handwheel is rotated continuously. Note down the maximum value displayed on digital screen. This is experimental or the actual value of crippling or buckling load. 11th, repeat the experiment for different lengths and different materials. 12th, repeat the experiment for different end conditions. Safety and maintenance. Never try to release a strut from its fixings, and when it is under load, always reduce the load force to 0 before you change or adjust a strut. Second, follow the instructions while using the equipment, otherwise protective parts may not work correctly. Aim, deflection in curved bars and davits. Delta is delta V subjected to vertical point loading. Theory, when force is exerted on the elastic object, work is done on it will deform. The work energy which is stored in the elastic object is called the strain. The work energy which is stored in the elastic object is called the strain energy. The elastic object will return to its original shape when the force is released. The strain energy can be caused by pressure, tension, bending, shear force, etc. Castigliano's theorem states that the deflection caused by an external load at every point of action of these forces that are deflection. By using the above theorem, we can determine delta H, delta V. Procedure: select the test structure for which a deflection reading is to be determined. Measure the thickness and width of the test. Procedure: select the test structure for which the reflection reading is to be determined. Second, measure the thickness and width of the test structure and health calculation. Second, moment of inertia I. Clip the load. Third, clip load flanger to the free end of the test procedure structure. Fourth, properly clamp this test structure to avoid any further relative motion. Fifth, the dial indicator is to be placed in such a way that it touches the free end of the test structure in both the directions. Sixth, calibrate both the dial indicator by setting the readings to 0. Seventh, start putting weight on load hanger and gradually increase for subsequent deflection values. Eighth, after loading the test structure, note down the deflection readings shown by dial indicators in the respective directions. Ninth, repeat process by applying different weight. 10th, compare the analytical and experimental values. Aim: first, to establish the relationship between applied load and horizontal reaction at the spot. Second, to observe the effect of load position